Am I audible in the back? Am I audible in the back? Is it better now? Okay. So, good morning. And let's start with what were we doing in the last class? What will be there in the start of the last class? We started with statistics of design, or statistics and the use and design. And once the first thing that we looked at was that the sheer numbers, the number of memory cells, the number of sense amplifiers, the number of units or design elements that we have in memory to qualify a memory for good yield. Plus minus 3 sigma does not put in amplifier. But if we write that one, that the object capacity is of the order of 16 megabits, we need to qualify plus minus 6 sigma. And if it is more than 16 megabits, then we need to go far beyond that 6 sigma extent. So the software group of plus minus 3 sigma, that is total 6 sigma qualification, or even the way analog circuits need to be defined or handled. The sheer numbers and the statistics things would indicate that those methods would fail if applied to memory design. So verification in memories has to be done very carefully, very judiciously, and by taking much larger variation extents into consideration than memory designs elsewhere in the design. That's it. Are you with me? Then another thing that we talked about was process capability. So there were two metrics in process capability. What were they? So we called them CP and CPK. So what did they represent?
CP represents the statistical distribution of the CPK tells about the centering of the
So if we assume that this function are Gaussian, and there are two variables that we could have, mu and sigma. One of these two characteristics, CDP or CP, looks at what is the possibility or what is the probability of movement of mean away from the target. Okay. And the other one looks at what is happening to the sigma. How big is the sigma? And you have to qualify a very large sigma, whether you will be within the target specifications of the process or not. So CP and CPK are in those terms measures of the two key variables linked to normal distributions, into large Gaussian distributions. Are you with me? So if you understand this basic, then what they mean, how they use them will be simple for you. Because I'm assuming you know Gaussian distribution. But then we moved on and we see that Gaussian assumption fails. Right? Why does Gaussian assumption fail? So the Gaussian assumption for manufacturing holds true. The Gaussian assumption which led to the formulation of CP and CPK still holds true. But when you are verifying the memory design, this does not hold. Because while the input parameters, input variables like BP, mobility, all that will be Gaussian distributed, the impact on output variables like current, leakage will no longer be Gaussian because the relationship is not linear. In leakage, the relationship becomes exponential. At other places, the relationship is a complex mix of linear and square, or there are secondary terms which start. Then there are second order and third order effects which start to come in. And therefore, as a memory designer, what you consider as inputs, what do you consider as inputs for your, let us say, self-time design? Memory current, memory leakage, for you, these are inputs. Cell current was one thing that you gave as an output for memory cell. Figure of merit of memory cell is cell current. As a designer, that is your input. This input is not Gaussian. Because the dependence on Gaussian variables is not linear. This. And that is why verification for memories or verification to include statistics in memories is not simply okay, do SS plot, do FF plot, and do something that can't work like that. And therefore, we looked at better methods of avoiding variations altogether. What we said was that instead of trying to mitigate the impact, let us avoid it. Because mitigating the impact may not be simple. This distribution is no longer Gaussian. So to mitigate a non-Gaussian impact may not be simple. Let's try our level best to avoid them altogether. And we've been talking about avoiding mismatches since the beginning itself. We were talking about common centroid. This was not last lecture, this was not last to last lecture. We talked about common centroid so earlier. We talked about common centroid, we talked about matching in terms of metal layer in which we're routing sections. The last class we also talked about replica path. So what is replica path?
That's the worst part of the machine. So I will clear the research.
So it lacks the real memory set. But to say that it lacks the work isn't about it. Because अगर आप हमेशा burst को ही track करोगे, you might have to get a very bad design. Okay, in the article that I showed you, I showed, okay, this will be the slowest memory cell, so I'm doing this. That doesn't mean that is the only thing that you have to do. I'm not binding you to that. Okay. So अगर आपने mentally अपने आप को burst के लिए बांध दिया, I would say unbind. Replica, essentially the word means that I will try to emulate, copy the same behavior as the real memory cell has. Depending on what kind of margins you have in other parts of the design. This may be the worst case, this may be a little better than the worst case, or this might require to be a little worse than the worst case. When I introduced replica design, I did not say that replica has to be the worst. Somehow you added that word. Replica simply went copy. Why copy? Because I want to reduce mismatch. That's it. Replica path. What we want to ensure through a replica path is, for example, for the read replica path is that whichever sense amplifier I'm talking about, that sense amplifier has the required input differential voltage. Are you with me? And in that context, we also looked at when we put the replica bitcoin in the center of the core and doing reset in one particular way or SAM in one particular way, versus when we put the replica path on one edge of the core and bring SAM in a different way, the worst case sense amplifiers that we need to qualify will change. Yeah. So do not fixate on burst. Oh, okay. Do not say that replica path is worst. Your only intent is the burst cell should also pass. You have to use replica judiciously so that you are able to track that burst cell. and ensure that this first step also passes, given all the variations that can happen. Are you with me? Any questions over here? Until here?
Also, I have the process ability. We said that we want 6 sigma on both sides, right, for a memory cell. Why are we choosing the formula for Canada? Just yes, a 1 6 sigma.
Because this formula of CBK, very, very good question. Have you understood this question? He's saying कि सर अभी अभी आपने कहा कि हमारे को 6 सिग्मा से ज्यादा क्वालिफाई करने की जरूरत है on each side. But CPK formula and the CP formula that you're giving me, they are only on 3 sigma. So this is a very good question because it makes me introduce a new topic. What we have not discussed until now is how are variations estimated? Okay, not for the modeling part, but in a running block, in a manufacturing block, how are variations estimated? So what you do is on a big wafer, you identify 7 locations. So do you remember what I talked about scribe lines? When we talked about wafers and dies in DVD, I talked about scribe lines. Okay. So on any given wafer, you can manufacture hundreds and thousands of chips. So when you manufacture those hundreds and thousands of chips, you also have to separate them later. Do you think separation will happen at a nanometer scale? For separation, what you need to do, you need to actually have a cutter which would cut the die. The cutter blade has some thickness which is far beyond nanometer scale, at least a few microns, hundreds of microns. So what is done is, in between any two dies, there is a space of a few millimeters. Millimeter or part of a millimeter. Okay? Depending on how good your slicing, laser cutting material is. But whatever it is far larger than a few nanometers. Has to be. Because wherever you cut, again, a different kind of stress will happen. So any active device should be far away from the perspective of those devices. At least a few hundreds of microns away from, a few tens of microns away from those devices. That is a requirement. So what you need to do is, you need to leave some space between any two adjacent dies. This space would then look like an array. And the lines of that array are called as scribe lines. Obviously, these scribe lines are fixed. They are cut away. So you cannot put anything that you would want to use in your SOC in the scribe line area. But you still can put something in there which you may want to use separately. What could be that something? That something could be some test structures which can help you track the health of your wafer. See, even as the wafer is getting manufactured, after every step, you have to test that is it going to the next step or not. Okay? See, suppose आपने gate oxide ले करा, you deposited the gate oxide. Now the intended thickness of the gate oxide was 10 nanometers. 10 nanometers. I'm really calculating. In advanced technology, it is less than 1 nanometer. Let us say 10 nanometers. But when you laid the oxide, it was put at 15. Now, what happens if the gate oxide is what happens to the devices at 80? See, the capacitance of the gate reduces. As the capacitance of the gate reduces, the control over the channel reduces. You need to apply much larger voltage on the gate to get the same kind of current. I'm going to basic physics. What is a MOSFET? MOSFET is a capacitor. You apply voltage on one side and control the channel on the other. It is all coupling. So if the capacitance is small, To get the same kind of current, you need a larger voltage there. What happens? VT increases. Now you know that if instead of 10 nanometer, I have a 50 nanometer gate, my VT has increased so much that I am out of spec. I don't want to proceed any further. I would jump that wafer that not there is. Why go and waste and design so many other things on it? Put so much extra cost, put so much extra time on it, and then say, oh, it was a very slow lot, so all the dies are going to the wafer. Only one die or two die can be recovered from it. Doesn't make sense. So you need to test at every stage what is the level or what is the scope of quality assurance that you needed. So such test structures are put in guidelines. Now tell me one thing. Now these guidelines, would you want to think of qualifying Six Sigma there? No, these guidelines you can use very big size structures, because what do you need to measure? You need to measure how thick is my gate oxide. I wanted a current of this much to be flowing in the transistor at this time. Is it flowing like that or not flowing like that? And these are big transistors, they're not very small transistors. It could be a range of transistors, but see, reasonably spread out range. Okay. And the count of such transistors is also not very high. Not just 2 samples, there 7 samples, 10 samples on a die, on a wafer. So when we are talking about the capability of a process, we are not talking about the statistics of memory. We are talking about statistics of these test structures which come in guidelines. That is why CP and CPP are qualified at professional space. Are you able to see this? Now, does that mean that process engineers don't need to qualify Six Sigma? Absolutely not. Absolutely not. Process engineers need to qualify beyond Six Sigma just to ensure that memories are functioning. You realize this? They have to go much beyond. But in terms of whether my wafer should go forward or not, just check where is it going. And for that, Six Sigma is there. So thank you for this question. It's brought in a completely new flavor and topic of the day. Anything else?
What we have the choice of placing the replica with towards the right. So why? What would govern this choice that we have?
Again, very good question, but you can reduce the cheapness yourself based on what inputs I gave you last time. I will help you do that now. So what were we looking at? When we were looking at the placement of replica line in the last class, we said that you could be placing it at the edge, that edge, or let us say this edge, and over here there is control, and from here SAN will go, or from here SAN will go. That is what that is. So what have you done? If you are tracking, if you're keeping the replica bit line here, if you're keeping the replica bit line here, the cells in the bit line can get selected from this side itself. So what are the delays that you're seeing on the replica path? You're seeing the delay of replica bit line, and then you are seeing the delay on the RC. Let us put it like that. Then you are seeing the RC of SAN. If you were to put this here, so you would first see the delay of a replica bit line, then replica bit line, then SAN. Are you getting this? So this, including the delay of replica bit line, is clearly a additional delay. Is it needed?
Yes. It would be too obviously.
Yes. How many of you think yes? How many of you think so? How many of you think yes? Two people. How many of you think no? Thank you. So what are the two things? And what's happening?
We can, because this is only delay, right? Then we can tune how many cells we have discharge also. So even if we have the first, we can change it on more cells, then we can tune the inverter. That's that you are saying exactly.
So what have you done? He's coming to the next step now. What Madhav is saying is at the next step. The first part was, do we need this delay or not? Some said yes, some said no, others were clueless. So let the clueless remain clueless. I'm not giving you an answer. I'm just leaving you with whatever you want to think. But you already understand that when it comes to arriving at SAEN, the worst case is sense amplifier should also have the required offset available at its inputs. Now let's look at the delay of a real memory cell. Real memory cell has one line RC, it has bit line RC in it, and then you come to the sense amplifier. Now let us see if the memory instance has only 100 columns or 1,000 rows. 100 columns, but 1,000 rows. Will word and RC be a significant part? But if your memory has 1,000 columns and 50 rows, will word and RC be a significant part? So can you clearly say word and RC? See, just this litmus test tells me that if I'm designing the memory compiler, which you will, if you are going to be a memory designer at any point of time, you will be designing memory compilers on. So this one thing is that if I'm designing a memory compiler, then depending on my instance size, I might need word line RC to be tracked. I may not need it to be tracked. So because depending on my instance, I may need it to be tracked. In a compiler, you will always track it. You may say, I don't want to track it for small instances, small column instances. So you may say that, okay, in that compiler, I will make a design range. That if my design, my memory instance that you want to generate from this compiler has less than 128 columns, then no replica word line. But if it has more than 128 columns, then replica word line should come. This is the design decision you can take. Now, on paper, ठीक है इसमें डालेंगे उसमें नहीं डालेंगे now come to think of it from the verification, just LBS verification perspective, DRC verification perspective, national perspective, everything. Now what do you need to do? You need to ensure that there is these cell, some particular cell which can connect replica or replica word line के decoder का replica row decoder का output directly to the replica bit line, or another cell which would take this output from replica row deck to the replica word line. एक दूसरा, because I want to track the replica word line, now instead of this abutment, I need to qualify this abutment also. Then there are no DRCs, no violation of this abutment. Are we able to see this? See, unlike standard cells where we always left half DRC in every cell, किसी को कहीं भी लगा दो, doesn't make any difference. In memories, we do a lot of sharing across the boundary. Now, as soon as you change the boundary across which you want to share, you have to redesign everything and show that every sharing interface is seen. Are you able to see this? So as a designer now, you are putting double the effort in designing the compiler. Are you able to see this? This effort has immediately doubled. Now what do? You may say that emails or very small instance also, wordline RC is not going to be a very big component. They can always track wordline RC. Then what I do is I will always have my replica on that side. See, my whole job over here is to confuse you. My whole job over here is to confuse you so that you now start to ask questions and start to explore towards answers. Move towards answers. Okay. So what have I done now? I have said that पहले मैंने कहा कि मैं यहाँ भी रख सकता हूँ, वहाँ भी रख सकता हूँ. मैंने आपको कहा कि नहीं. Safer appears to be there. Less effort appears to be there. Are you with me? Shall we take the story forward? I have put the replica bitline on the far end of the array. So sense amplifier trigger will come from the far end to the control region. This is the only path now. So now look at when will I generate reset? I will generate reset after replica word line plus replica bit line plus SAN full RC. Now then go back to sense amplifier or wherever. We said that when the reset comes, I trigger sense amplifier and I also decouple the bitline and start the charge. Now, do you realize that in this design, my sense amplifier has gotten triggered, but after all the sense amplifiers have worked, only after that I can trigger pre-charge. So in terms of my reset time, this is not a good answer. A good answer would really have been if I put the replica one here of itself, so that SAN and reset are generated at the same time. Are you getting it? So a good answer would have been the replica bitline coming next to the root control region itself. Because when I keep it far away, my timings are suffering. Some timing is suffering. Is this evident to all of you? Anyone, any conclusion? Yes.
This one comes to if you keep it to the very right first, then what will happen is that the sense enable or all those things can still have to wait for this
sense enable will come, please have to wait. Recharge comes from reset. So reset, you can get only from the control region. Until SAM reaches the control region, I cannot start the reset. I cannot start the recharge.
Well, the sense enables will be the same for all these sense amplifiers.
Yes, but there is RC delay coming in here. Is this magically traveling from here to there? No. There is an RC here. This RC can be hundreds of picoseconds.
And we will do on reset time because
reset time, we are losing on power also because word line continues to be on. Now, see, you have already sampled the sense amplifier, but bitline is continuing to discharge because reset has not come. The power is also being lost. It's not just hanging, it's also power.
So we could also have a higher power than this considerable short circuit current. Maybe in this recharge starts before maybe the almost sense enable is turned on. So it could be some bitlines are not being decoupled.
Yeah, this when you are putting it next to the control region, that's the master.
So because when the reset needs to be turned on at once for the whole thing. So
we are talking about magic here. Nothing magical is going to happen. There is going to be an RC delay. There are wires which will carry any signal. Wires have RC delay. Don't think in terms of schematics now. You're not working on standard cells with touch antennas or something. Talking about wires which are hundreds, thousands of microns long.
Just confirm one thing. Why do we have to? Why does reset timing suffer in this case?
Because now, in arriving at the reset, I have the full SC and RC coming into picture. Where I could have actually given reset right after this without impacting anything. Are you able to see this? If SA and timing had not come in the picture, even then I would have given the reset. Now this delay is extra. And this delay is taking extra power consumption also. Is that clear, everyone? Now we come to the next part. This question was, if I have this replica bit line next to the control region, then
The recharge will turn on.
the recharge will turn on, but sense amplifier is not being compared here.
Maybe the most rightmost sensor has not yet decoupled the bit lines.
So now this is a race condition. What we are saying is that SAN over here should arrive before recharge reset. That's all that means. This you can handle. Handling this race condition is in your hands. What you can say is, okay, in the generation of SAN, I have 1 inverter delay. In the generation of recharge restart, I have 3 inverters delay. By design, this functionality is taken care of. That's what you can do now. It's very controlled. But now, but you've saved on power, you've saved on your improved overall dynamics also. Delays are managed. We already talked when we were talking about IO circuits, we talked about so many race conditions. Huh? We talked that word line recharge, bit line recharge to turn off before word line gets selected. Talking about so many race conditions in memory design anyways. Are you realizing we've been talking about verifying and race condition and everything since the beginning? Again, so not new. So race conditions are handled by me, and this you can handle. Kinetic dynamics are saved, power is saved.
But then there is some rules of the replica, putting the replica on the left side. But now, anyways, we have to manage the next step.
Yeah, like that. If I have not given you this status, would say many in this. So I have to save, I have to be safe, and I will put replica on that side. That side only. And that was how memories were designed initially. When the technology did not start, when the technology stopped giving us the gains, then designers started to think, how do I now squeeze out any gain? I'm already taking you through that journey very, very fast. I'm kind of speeding it up for you. But for tens of years, that part was only used for designing. Cloudless stuff. Now, see, what we are now observing is, and think of it, those of you who are doing the creativity course, I will reflect. What I'm saying is, I want the RC of word line to be there. When do I want it to be there? When it is a large column class. But I do not want it to be there also. Because when I'm talking about triggering the reset, I do not want that physical distance to appear because SAN cut RC changing. So how can you ensure that you have word line RC there in lecture but no SAN RC? So what you do is you say, okay, word line आप भी जाएंगे यहाँ से वापस आ जाएंगे. You get full word line RC. You get full bit line RC. But SAN RC is avoided for reset generation. Are you able to see this? Do you realize that this is a geometric play? This is a play on shape of something. In our linear thought process, some एक तरह से solve. But when pushed to a corner, we start to apply multiple instances. So we've applied the Mendel's principle of new dimension appearing and symmetry in synthesizing things. Are you getting it? So in most modern designs, you will see that Whirlwind is tracked, it's brought back, and then it triggers a replica pipeline. And now do you realize it is very simple? If I say that, okay, मेरे को छोटे columns से for a very small columns instance, I do not want to track replica bird line, I will say, okay, just instead of tracking everything directly, one छोटू सा extra cell, no new abutments introduced, nothing new introduced. And again, are you able to see this? See, you will see designs यहाँ पे replica मैंने ऊपर दिखाया है. You will see design यहाँ पे replica is shown here. You will see a wide range of designs. And SC we also had a design यहाँ पे SCN was not triggered from control region. We said, okay, why add this RC? I will have my replica word line. So replica word line was right next to the IOs. And we said, from this replica word line, I will have a small mini bit line coming in, which would trigger the locals and amplifier there. So what have you done? आपने SAN triggering के अंदर भी SC and RC को हटा दिया. Are you able to see this? So this was also one design that we made. There, your replica word line is moving, and simultaneously it is also generating locally. In every IO, it is locally generating its sense amplifier trigger. So this is also a design. Realize replica path के अंदर ही कितने सारे तरह के design evolutions और design innovations आप कर सकते हो. Because replica path is the spine, it is the backbone of the memory. All timings for CP2, SAE and timing is determined by the replica path. Very same. So access time, cycle time, everything is governed by the replica path. And you somehow want to innovate on this axis, then as much you can out of it, so that you have a memory which has a very good ET. Are you able to see this? No. So what we did was we had something going up and generating a signal which would trigger the bit line discharge. Then locally replica word line would get generated. Again, as a designer, you have to play and ensure that all the pieces of the puzzle match. There is no one else. Which is a very small row instance, between RC is not of consequence. As a designer, you should feel free. As a designer, I am empowered to play around. As a designer, be empowered नहीं feel alone. So what are you talking about? So you are just being dummies. Dummies को तो बड़े easily AI replace कर देगा. If you are replacing yourself with AI or yourself, that is a different thing. So yesterday I was talking to Rashmi, and she said, "Anuj, there is no dearth of jobs. I see many people struggling for jobs." She said, "See, they are using shortcuts through their entire fintech life or enterprise, and now they are trying how that jobs." So she said, "We brought HCL Tech twice. HCL Tech first came with a separate market and we would take these. Second time when they came, they said as many people. No boundary, no limitation. But students were not able to answer even very, very simple questions in the interviews. Yeah. She gave me samples of 1 or 2 questions. Software. So, very basic questions anyone could answer. Yes, that is what I'm saying. Anyone could answer, but they did not. ऐसा कैसे हो सकता? She said, I have talked to a few of them. And you know what they do? क्या? they use the power of AI very effectively. अच्छी बात है ना, तो AI को अच्छी तरह use करते हैं। नहीं, सुनो तो सही। So what they do is, any queries, any questions we give them, anything we ask them, they simply use Google Lens and ask Google Lens to find an answer. See, now copy paste. I do not know how many of you are doing that, but this is what she told me, that okay, people have been doing this. And as a consequence, they're able to get good marks. They're able to get good GPA. But they have already become slaves of AI. And she said that पता नहीं इस बार बहुत सारे जो भी कंपनीज आई अपनी प्लेसमेंट और देने के लिए बातें बहुतों ने, not one or two, many actually told students that if you think you can use AI to get some job done and you are preparing for your, or you are helping through your BTech learning or MTech learning in that manner, then you are not needed at all. AI यूज करना तो मेरे लोगों को दिया एंड अभी उसके लिए लोग चाहिए थोड़े टाइम में तो एजेंटिक AI आ जाएगा, वो भी नहीं चाहिए होगा, सो वी विल नॉट टेक इट. बट इफ यू नो द बेसिक फंडामेंटल्स then there is some scope for us to hire. So this is something that I wanted to share was I felt that many of us who are here in this room might also be starting to become dependent on AI. Perhaps even very basic things. It's a very fast way to get things done. See, all these summaries, I have written in 5 minutes. I can use it because I know this topic well. These summaries have been created from what I taught you. Do you realize this? Me using AI is a different thing. And you feeling like, or you having the freedom to use it. You have the freedom. But if you use it likewise, you are shooting yourself an input. So be careful. And that is why I'm saying that my intent over here is to confuse you. Because AI is not confusing. It gives you such a solid answer that आप कभी doubt ही नहीं करते कि ये answer सही है कि गलत है. This is the biggest problem with AI actually. And that is why you also very comfortably start to use those answers in your answer script, and mostly they are right. It's fine. But then what you have lost is the capability to think independently. To deduce something independently. To arrive at answers and new possibilities independently. But I can tell you that creativity is one thing that is going to differentiate people for their career growth going forward. Because a lot of hard work, a lot of tooling work, a lot of that, slogging work, then it is vanish. But those of you doing the creativity course have been insisting there that these tools cannot be applied by devices. To apply creativity tools, you have to be an expert in your technical domain. Then these tools come handy. So आपको creativity ही बचाएगी, लेकिन उस creativity को भी बचाने के लिए, like it can help you. You have to be technically strong. You have to have good understanding of topics. So more and more, I'm convinced that the questions that you should be setting in the assignment that I have given to you yesterday should be about checking understanding. So please make good questions. Let's check understanding and not just knowledge. Yes. आज करने का असाइनमेंट फर्स्ट का पेट का तो मैं 22 शाम का करूंगा तो भी तो सिर्फ 2 घंटे में कैसे करूंगा. अभी तो बहुत सारा टाइम. दो क्वेश्चन ही तो बनाते हैं, शॉर्ट आंसर क्वेश्चन एक लॉन्ग आंसर क्वेश्चन होता है. So, replica path. Any more questions? Clear then? So, replica path is a hotbed of innovation. Lots of innovation can happen here, and whatever you innovate here can have an impact on both performance and quality. Now we come to the, and what was the next thing that we discussed? So, okay, one more thing that is there on this slide also, which we discuss in more detail in the next one, is that while we are talking about this replica path and while we are talking about matching of word line with SAE and they have to be in the same material so that they track each other, all those things, while we are talking about all that stuff, we also know that failures are not only because of design. It is not just design weakness that leads to failure. We also, in the last class, towards the end, थोड़ा सा आपसे extra time request करके मैंने post कराया the topic of repair. और फिर से that if I have one extra Stephanie is what? In vehicles, Stephanie is the term used for extra tire. Right? If something happens, one of the tires on which you're running bursts, you can replace and still continue your journey. So we can do something like that in our memories also. And that can help us mitigate at least silicon defectivity. But if silicon process improves, sometimes, somewhere, I will also be able to mitigate design defectivity by using these spare rules and problems. So, redundancy in those terms is, while it starts from, and the most important objective of putting redundancy and repair is to recover from defects, hard defects. But by the very virtue of it being available, if I am not handling hard defects, I can also consider using it for repairing design weaknesses. Are you able to see this? So, redundancy, as we looked at it, that was more about hard defects as they appear at the time of manufacturing. But when we will go into the test part of it, in this course of memory design and test, we'll talk about testability and test and all those things later in the course. As we go there, we'll also see that the requirement of repair may appear later in the life cycle of the product also. See, आपका एक contract अच्छा नहीं बना. At the first run itself, you know this memory set is failing. I need to repair it. Now, आपका contract अच्छा नहीं बना, लेकिन बहुत बुरा भी नहीं बना. क्या होगा? All your tests will pass at PCB. All your tests. So, even though there is a weak memory cell, the tests will pass and you will be able to get a memory going. You can ship it to the customer. And customer will, so automotive, you remember I told you about 0 defect at 0 kilometers in automotive. That's a very strict requirement. So for automotive also, this means that, okay, I have 0 defect at 0 kilometers, my car will at least go out of the showroom. But now imagine, after 6 months of operation, because this was a weak contact or a weak VR, weak ka matlab, okay, there is a connectivity, but the resistance is large. So if you look at the DRM, you will see that the resistance of VRs and contacts is really tremendous. If we vary from just 1 ohm, so a good VR would have only 1 ohm of resistance, to something like 1K ohms. 3 orders of magnitude. So, suppose 1K ohms ka bana, actually 1K ohms ka bana, to bhi koi problem nahi hai because it is still within the design space, within the DRM space. Some VR got fabricated at 10K ohms. Does that happen? See that 1K ohms is the plus minus 4 sigma, 4.5 sigma, some kind of specification. That doesn't mean every VI is going to fall within that range. There will be VRs which will be out of that range simply by the numbers of it. So many VRs and contacts. Many, see, हमने कहा billions of memory cells. How many VRs in every memory cell? So, multiplicity of VRs in just the memory cells. So, on a chip, huge, large number of VRs. So, they are going to be outliers. This one VI is weak. One contact and weak. What happens? Its resistance goes up to 10 k ohms, 30 k ohms. 50 k ohms still at the time of testing it worked. But since it is very high resistance, you want to flow X amount of current through it. It will keep on getting heated. I square R physics. And when it gets heated, this resistance increases. And then, you remember the last lecture in PVD? We talked about failure modes. And we talked about the failure mode called electromigration. What was that about? So because of Replica and one-sided flow of current, copper atoms will move. And where there was a 50 k ohm resistance, there were already very few copper atoms. This is the part that is getting heated up. So these few copper atoms now are more mobile and they will move. So what happens? Very soon you will have an open there. That is what is the rectification. So you had a working time. Let's send the car out. And now 6 months down the line, this weak contact came away. Now what do you do? When you come back, ask the vendor, लड़ो उससे, कार के सर्विस स्टेशन पे जाओ, पूरा मदरबोर्ड चेंज कराओ. Or what is also now offered is in-field repair. What does the phrase in-field repair mean to you? So what in-field repair means is that if your chip fails in the field, if there are available stepneys, it will automatically make it. I have to have extra control logic and state machines in my soft design so that it can test my memories every now and then. And if something is failing, it should also have a mechanism of triggering repair systems, repair circuits, and revise the chip automatically. So this part we have not discussed in the last class. This part is not discussed, but this part is not being discussed even in the recorded videos. This part is very, but it is a very important advancement that has happened. And this is not new. This advancement is very old. We've been offering and field repair to things like Scientific and Atlanta, which would make network routers. Because see, after a router लगा दिया, अब आपका chip fail हो रहा है. अंदर resources हैं भी, repair resources are there. But you have to put the entire network down. You have to remove your router. That's not acceptable. So network routers have been used, and once this common major business started to use it, many other critical applications also now want to use it, and they use it. That okay, I'm putting extra redundancy, repair it in field. As we come to more advanced technologies, wires are the problem. Wires are the reason of failure. So all of this becomes all the more relevant. Now for memories, we talked about two kinds of repair mechanisms. We said that the structure of a memory cell and the very fact that we have much denser rules inside the memory cell. What are we doing? The susceptibility of failure in the memory IO region is much higher than the failure in periphery region or elsewhere. Are you with me? So we said that memory-related failures can be majorly recovered if they can simply replace a pair of rows or a pair of columns. We're talking about row redundancy and column redundancy. And we also look at the different consequence this choice has on ordinance, power and regulation. So, as you said area, let's start with area. Which one consumes more area? Column area. Why?
People share all the
Shift all the columns comes to cover. Why are area comes there?
equal sometimes.
I guess that is little amount of area, one greater than equal to comparator and if it twice the area of the equal to comparator. What's the area? What shifting required not solved. Okay. This is one very, very big point. Because I was at this when you connect the masses there, that is what we also said. You're missing a big point actually. Relevant in the room.
Address people are also.
Address put it also there. But he Maria. Or yes, हम एरिया की बात कर रहे हैं अरे यार स्टार्टिंग एरिया बोल दिया उनका इसकी बात कैसे डाल सकते हैं लेट्स स्टार्ट विद एरिया व्हाई डज कॉलम रेडंडेंसी टेक मोर एरिया कंपारेटर सो दैट तो ग्रेटर देन इक्वल टू कंपारेटर थोड़ा सा तो बड़ा होगा इक्वल टू कंपारेटर मैं उसी के रखना ना पिक करें So you can make a sense amplifier which is slightly larger than another sense amplifier. What about sense amplifier area?
So is it due to because it requires that every column is required?
Yes. In row repair, only one comparator only, and that comparator is an equal to comparator, greater than comparator, whatever. It is just one comparator that we need. You compare address of trailing row. If it matches with the correct address, you say, okay, instead of going there, go there. एक बार आपने उसको बस ऐसे reline करना है. One comparator. In column redundancy, at every column you have to check if the failing address is smaller than my address. Because if it is smaller than my address, I have to shift. Are you getting it? This is the major reason why we have larger area in column redundancies. Now you may say, sir, ये सारे comparator क्यों लगाएं? मतलब see, suppose आपने कहा कि मैं first column पे comparator लगाता हूँ, second पे नहीं लगाता. Second one is available to you. The only thing you can do is, okay, I will have an equal to comparator instead of greater than equal to, and I will somehow also take the input from my previous stage. If my adjacent value had an equal to comparator 1, then even if my equal to comparator is going to be 0, because पिछले वाले का 1 था, my output is going to be 1. Now, since my output is going to be 1, the next one will also see that, oh, this output 1 है, मतलब I also have to shift. Then the next one, oh, my left body has 1 as an output, so I also have to shift. And this ripples. So what that then does is, you save the area, but you've taken hit on performance. Which performance? Excess time is higher for column redundancy, that is just a little higher for column redundancy because of the extra ones. This is not excess time. This is redundancy setup time. At the time of power up, when your memory starts to receive the failing address again, this ripple shift has to happen again. Every time you power up. So there is a wait period before you can start to access the memory again. So this leads to a system constraint. In terms of memory, regular timings, what is excess time? Only one extra must come in the past. No impact. So column redundancy is better in terms of timing. To save area, you have traded off redundancy setup time or power up time of the memory. How many times do you need to power up a memory? Not many times. So if that is the case, you can use ripple. Greater, not greater than equal to, only an equal to comparator. So you'll save some area, but you still have lost the area because you have equal to comparators in every IO. Okay, area is still far larger than row redundancy. Are you getting it? What about row redundancy? Area becomes will go better. Let's look at performance. What goes for a toss? Second. Why? Because every incoming address now has to also go to a comparator. That comparator will decide whether it has to go up or to the repair. So address second time goes for a toss to the comparator. In terms of power, both would be equivalent. Except that power consumed during setting up of column redundancy is going to be higher because more comparisons are happening, more leakage is coming in. So those are secondary impacts, not the primary impact. It does not change much about the dynamic power of the network. Are you with me? Any questions about memory repair and memory redundancy? Yes. You can only recover one. So when your memory is split into left memory and right memory, you can only recover one column on each side. Otherwise, you can recover only one column. Yes, as many number of comparators you put for the room, you will be able to recover as.
In general, how the first scale have this first area. You know, you look at one failing row, okay, but we have many rows on every.
So this question is one pair of repair rows sufficient? Is it the right way to frame the question?
Yeah. What is the number?
So, see, do you think that process engineers will survive if they have lots of failing memory cells? So process engineers are direct. And you have to ensure some yield, some level of defectivity has to be arrived at so that you can go into production. When you are in production, the target that is given to memories is that you should be able to recover from one defect. It's a very large memory, as we was asking. You may want to have two repairs. Okay. So two repairs means I mean if it is low redundancy, I will need to have two heading addresses coming in and two compile addresses coming. If it is a column redundancy, then you may say, okay, one repair on left, one repair on right. Now, if something fails, or two columns fail, or two independent defects come on the right side, you can't recover that. But that's not the spec. The spec for memory is one defect, or at most two defects. So I would say I would want to go by the spec that the technology gives, because that's the target that they have. Because if I start to go beyond that, I degrade the PPF. So this would come to you as a specification. When we talk about UPH repair, in that case, it is not the technology team that will give you the spec. The design team The soft design team may also give you a spec that I need 3 repairs per minute. First, based on their previous experience, or based on their interaction with the process, or based on their internal know-how from a application, they might know that okay, in this particular technology, big defects are very common. Or that the phase in which we are in the process today, big defects are very common. While they may be taken care of in the future, I want to hit the market fast. There's this time to market constraint that I have. So instead of just 1 or 2 defect repair, I may want to repair 4 defects. So that I can hit the market fast. So see, time to market is a very, very important thing. Extremely important. If you do not reach the market on time, the competitors will take all of it. So many people in field repair are easily marketing extra repairs just so that they can keep their customers with them. Come to think of it, Apple already announces Apple Days months in advance. Why? Because it's a marketing thing. They want that on this particular day, I will want to release my new Apple phone. And people are now waiting outside Apple stores in anticipation. But not. Now suppose Apple के अंदर आपने ये कैमरा मॉड्यूल दिया जिसके अंदर एक मेमोरी भी लगी है. And आप फिर वो one memory, I need to 2 months, just 2 more months. You think Apple will wait for you? If you are not designing to Apple 6 months before the product release, you are not going to hold that model at all. Are you saying this? So if you have not hit the market on time, you lost a major chunk of your revenue. You can't afford that. Whatever you are designing, IO design कर रहे हो, processors design कर रहे हो, कुछ भी कर रहे हो, time to market you simply cannot afford. Time to market is nothing. So please late assignment, 1 hour delay. I can accept it, but that is not how it works in the industry. So, anything else? Repair redundancy. Okay. So now we do not have the time to start the cache subsystem. We'll start that after next. That is not an issue. If there are any questions that you may have about your projects or any other aspect of the course, we have another 7-8 minutes. We can handle it. So शुरू में नहीं करा ऐसे कैसे कर सकते हो आप हमारे साथ the project history the project history that's the answer process. So all of you always know that you have the flexibility to choose the project within this course. Right? I mean, choose the project means propose a project in this. So if you have your ideas, have you already proposed your project ideas? So those of you who have not proposed project ideas, let's do the reviews within the next months. Anything else? Project teams are already finalized about that stuff.
One of the general questions will be about what is all these corrections and all of this. So when the design is going on, so these all will be designed parallelly, or is there like there's some design of floating or that is already created and the designer will be sort of around that specific.
So this question is more about the way memory design happens in the industry, right? So see, I do answer this little. For memory design projects, it's typically time at a company that a team may get is of the order of 6 to 8 months. And you design a new memory compiler, not one memory compiler is 6 to 8 months. In my experience, of that 6 to 8 months, first 2 months go into evaluating the design choices. First 2 months. That is also at times the 6 months and the 2 months and at most 1 month. Okay. I have this particular compiler in the previous technology, or I have a similar compiler or a good working compiler in the same technology with this spec. Now I am being asked to design a new compiler with a different spec. So I can evaluate which things I can reuse from there, which things I really need to redesign because of the new specification that I have received. This is a decision that you will make within the first 1 month or 2 months of your design cycle. So look at these new cells and these new I can acquire or adapt from existing solutions. In a new technology, you know that you have to design everything new. But because again, the time cycle is limited, you have to lay out everything and schematic everything. So you might not go to a new design architecture or lots of innovation in the circuits in the first compiler in your new technology. So in the first compiler in the new technology, you will probably only copy paste the architecture or design style of the previous technology, whichever was best in the previous technology. You copy paste that and you will ship it out. Again, secure and fast. Minimum viable product की बात कर रहे हैं. That's the minimum viable product. Now you sit back and say, oh, my customer expected 20% performance gain. But when I use the same architecture from previous technology in this technology, I have lost 2%. So I now need to improve the performance. Now I evaluate. So this is the next compiler that you're designing, and that is what I'm talking about. Now they will look at, okay, first 2 months, you're evaluating which part I can change, which timings, where is the one analysis which is leading to limited speed. And you focus on those areas. You redesign those areas. That's a new compiler. And by the time they will go into production, your new compiler will be ready. So first 1.5 to 2 months about designing or making these design evaluation and choices. Next 2-3 months about really designing, schematic, layout, everything in parallel. So you will have a team, depending on how many new things you talk about, you will have a team of up to 8 people, 9 people, with 10 at times. And you will have lots of other teams working with you. For example, last semester we had Sir coming and speaking about automation. He is not a part of memory team, but he is logged into the memory team for the duration when we need software design for the compiler. So such people will also be there. So total number of people involved in a memory project could be more than 15. But dedicatingly in your memory team, it can be up to 8-9. If the updates are not big, there's 2 people, 3 people may also be there. But if it's a new compiler, very different spec, you will typically have 8 to 9 people. So first month, 1.5 to 2 months about design architecture, circuits, replica upper, niche, bit lines, all that generally first 1.5 months, 2 months. Then implementing it in the next 2-3 months. Remaining 3-4 months actually verifying and correcting all marginalities, all race conditions, ensuring that set damning path is accurate, set damning path gives you the required margins. So a lot of time goes in verification. That's why I've been talking about verification from early on. So verification is very important. So all this work happens in family, a big thing, usually a big thing. Any other IT you see, small things. Pura library, आपके 3 लोगों पे नहीं बना देंगे. 500 cells, 1000 cells library, 2-3 people, not more than that. Memory is 1 memory compiler, 7 people. Anything else? You're asking, can I use secret marks now? Where are you? by IO. And so that what that means is suppose you are at month 16 and you say that okay, I will replace the entire IO, not just the columns. And then you're saying the same area in the comparator region, but you've added 14 extra columns that will now be required to replace. Look at it like this. Let us say I'm just showing 4 bits with lines over here, but let us say there are 16. So let us say this one. Wait. If you are offering column redundancy, then what you will do? And here is a max. What you will do? You will say, okay, let it be like this. Instead of this, let this go into my marks. And this one will also come here. And I just need one extra column here to complete my repair. Are you able to see this? Now suppose you said, no, I do not want to put a comparator before the marks. I will put a comparator after the marks. So if this fails, you are saying this is failing. So now you are replacing this output into this memory, this output into this IO, this output into this IO. What does it mean? That on this side, this is not how it works. You will have to have entire 16 columns repeated to be able to drive this. So you saved area in this region. You have lost area in this region. So you now have to add 14 extra columns and maximum to be able to do an IO set. This is also done. This is called as bit slice redundancy. The entire bit slice is shifted. This is also done because it's a very valid trade-off. So all these combinations, see, I cannot give you every combination in the class. You have to experiment and come up with new combinations. Many of them may already exist, otherwise you will create something new. Okay. So all the best and prepare well for your mid-sem exam. Do well. All the best. Thank you.